Good evening, everybody. Absolutely delighted to see the lecture theatre looking so full this evening. We were expecting lots of people, but we've absolutely knocked it out the park. It's our record attendance for the year, so really, really delighted to see so many of you struggle through wind and rain, etc., to get here, and no doubt foregoing a Christmas party, instead choosing to spend your evening at IMechE for our prestige lecture, which is fantastic. We're not doing a live recording, but this event will be available online afterwards. So if you're watching online afterwards, you're very welcome too. So I'm Alice Bunn. I'm CEO here at the institution, for those of you who haven't met me already. It's my absolute delight this evening to be able to introduce the Thomas Hawksley Prestige Lecture. So for those of you who don't know, we have a number of prestige lectures throughout the year which are named after engineers who have done a phenomenal thing for our society. And we're really delighted that we think this one's very fitting for the topic we've got this evening. As you know, Thomas Hawksley is best known for his work in water engineering, so pioneering the supply of clean water for Nottingham as far back as 1830. And he's largely regarded to be responsible for the supplies of Liverpool, Sheffield, Nottingham, and many other industrial sites, which is why the Dictionary of National Biography states that there is scarcely a large city in the kingdom which did not make use of Hawksley's services at one time or another. So the reason I think this is so apt is, by all accounts, clean water is something that we largely take for granted these days. We don't really think about so much. And I think that's going to really chime with some of the really innovative work that we're going to hear about tonight, which in the future may well be one of these things which we don't really think about very much and we take for granted. But before we hear more of the main item for this evening, it's my great pleasure to introduce the organiser and really the driving force, I would say, behind the event this evening, Carolyn Griffiths. So Carolyn is the institution's 132nd president and has been a lifelong contributor to the IMechE, in particular its railway division. I'm sure many of you in the room will know Carolyn. Tonight's event continues this long lineage of helping the IMechE drive change and showcases the power of our volunteers to influence the profession. We've said it many times, it's very much a member-led institution. She's a fellow and a trustee of the Royal Academy of Engineering and was a board member of the Engineering Council. She was the founding director and first chief inspector of the Rail Accident Investigation Branch, which was established in 2005. I think there are some colleagues from that time in the room again, we were talking earlier. And she chairs the Rail Group for the Parliamentary Advisory Council for Transport Safety, with whom we are grateful to be partnered with for this event, and have previously been for the 2019 seminar on driver and pilot alertness. So, without further ado from me, please give a very warm welcome to Carolyn in the usual way.
So, good evening, everyone. I imagine everyone here will agree with me that autonomous and semi-autonomous systems are no longer a futuristic concept. They're already around us. We can see them operating in various walks of life. The potential for autonomous systems, greater incorporation of machine learning and other AI, I'm sure you'll agree, is enormous. And under the right conditions, this has the potential to transform how we live, to stimulate the UK economy, driving productivity, creating new jobs, improving the workplace, and helping those experiencing disabilities have a better quality of life. This technology has come into sharp focus for most of us because of the development of the autonomous car. But it's already been and continues to be adopted in many other sectors: the process industries, aviation, rail, and health services, for example. This evening, we're privileged to hear from Sarah Sharples, who's the DFT's Chief Scientific Advisor, and who is an expert in psychology and human factors in engineering. And we will hear from a number of other prestigious experts who will later join us in our discussion panel. And I'll introduce Sarah and those on our panel in due course. Now, this evening is not a debate. This is not a formal debate, but you'll soon see it is part of a much bigger and, in my opinion, a very pressing debate surrounding the issues of humans and automation and safety by design. But having said that, and somewhat controversially in debating style, I want this evening to raise some challenges with you all and to consider these challenges as we listen to Sarah and the discussion that follows. But before I go there, I'd like to explain why I personally called for humans and automation, safety by design, to be the subject of the Thomas Hawksley Prestige Lecture 2024. Firstly, I want to put out there, I'm not a human factors expert, nor am I an automation design engineer. I'm an engineer with an operational background, and as Alice said, I chair the Rail Group in the Parliamentary Advisory Council for Transport Safety, PACTS, and I founded the Rail Accident Investigation Branch, RAIB. But it's with this experience that I elected this evening might examine humans and automation, safety by design, with the following issues in mind. In my role at the RAIB, where I saw things and accidents that happened and when things went badly wrong at the person and machine interface. I saw accidents happening because persons lost concentration, their situational awareness, they were overwhelmed by tasks, they were fatigued, or otherwise unable to respond to unexpected events. Key issues for consideration in designing autonomous systems where people are still somehow involved. And I, like others, began to, and I still, question how can we better design for safety when we have imperfect understanding of human performance and where such performance not only varies with the individuals, but over time and according to circumstances, and also in connection with an automated system that itself may change over time with machine learning. That's quite complex. So in this context, no matter whether you're an engineer, a policymaker, a researcher, a human factors expert, or a regulator, I invite you this evening to consider the following specifically engineering-related questions when considering human-centered autonomous systems. Firstly, whether our hitherto traditional methods of engineering design and development are still fit for purpose. Whether the way in which we test and validate those systems and regulate their development may also need change. And finally, whether the education of engineers and human factors practitioners therefore needs to reflect changed practice. Now, some of you may already have been engaged in such a debate, others may not, and still further, some of you may disagree with what I'm about to say, but I welcome that. But I'm not alone in believing that we are yet to establish a widely accepted and shared best practice in approaching design and assurance of human-centered automated systems. And against that, we will be able to develop, assure, regulate, and educate. I propose there is, in all probability, a strong case for change. We're not going to solve these issues here this evening. Of course we're not. But my hope is that what we hear and the opportunity to exchange ideas will support and add impetus to answering these questions and other questions around humans and automation, safety by design. I'll further elaborate, but briefly and from my personal perspective. Let's start with human factors research. It seems to be plentiful from where I'm standing, and within that research there are common threads where people are finding that there is a support for my hypothesis that we need to change the way we go about design, testing, and validating the systems we're considering here tonight, and therefore also how we might regulate and educate. In recent years, the National Engineering Policy Centre, led by the Royal Academy for Engineering, but in collaboration with 42 other engineering-related organisations, including the IMechE, has brought together the opinions of practising engineers from all different engineering sectors, and they too identified a wide-ranging need for change. And I'm aware of a number of organisations in the industry who are working with these challenges as we speak, and so will have much to offer. A traditional design process, as many people here will recognise, is plan-driven, stage-gate-paced, and dictated by engineering requirements. Can this, or even a more agile software development protocol, be optimum or even valid to design human-centred automated systems which engages AI? A system approach to designing safety is far more complex, where the system has a degree of autonomy itself, but still needs human intervention under certain circumstances. Not only does the design have to take into account the changes in the operational environment, but it also must take into account the variability of human performance, their age, their culture, their experience, and their capabilities, but further complicated by each operator's performance varying still further with time and circumstance. And add on to all of that the variability that may overlay all of this arising from the very same machine learning. Now, I've read a number of research papers that suggest that a more fluid and iterative design process that involves human factors expertise in the design team, human factors experiments, prototyping, simulation, and examination of requirements, that's really what should be happening at our design development protocol. But this is a very different approach to that which many of us have been trained in our earlier careers. But is this the new standard? And where is it captured? And can such a protocol be the baseline against which delivery of a competent design is evaluated and regulated? Testing of safety-critical applications typically assumes that you can predict all possibilities of failure. However, authorities on this subject say this will not be achievable for autonomous systems, since all the possible situations that an autonomous system might experience cannot be foreseen. So verification of autonomous systems can be challenging, especially for those systems that learn and adapt as they operate, and they also change according to their environment. So this takes the decision-making beyond initial designed and verified systems. AI systems are trained and operate by inferring patterns and connections in data. Sometimes it's difficult to detect these, and then the AI can develop the ability to perform new things of inference, not directly envisaged by their programmers. So you can see this is a whole new world for design and developers. And as such, there will be a different need for verification or different means of verification. To manage the continued learning from both the individual system and those connected to it may require a move towards a program of operational verification. And all this then additionally has questions around it about how safe and resilient human-centered automated systems need to be before they can be trialed and then deployed at scale. So then thinking about regulation. So if all that change has to happen in design, development and testing, it does suggest that we might want to have some different regulation protocols. So we do need a clear framework against which to regulate. We do need a clear framework, which I'll come on to educate. And we do need that framework to be cross-sector, I would propose, so we learn from each other. There's no reason why it shouldn't or couldn't be cross-sector. So we need to start collaboration. And meanwhile, there are ethical considerations and public acceptance issues, but we can't go into that tonight. It's a lecture in its own right. So if there is a need for new standards for design and development, if there is new standards for regulation, then this also suggests that we would train our current and future engineers and human factors experts in a different way, meaning our engineering degree courses, technical training, professional qualifications might all need to change. And similarly, the training and qualification of human factors students might change too. And here we are, as engineers, worrying about the supply chain of engineers for the future. But if we're to have multidisciplinary teams, then what about the supply of human factors experts? So I hope my opening remarks give some food for thought, and I'll be very curious to know what you think. So tonight, as I said, we're very privileged to have with us Professor Sarah Sharples, the Chief Scientific Advisor to the Department for Transport. Sarah is a Professor of Human Factors in the Faculty of Engineering at the University of Nottingham. And from 2018 to 2021, she was the Pro Vice Chancellor for Equality and Diversity and Inclusion and People. She's led research in transport, manufacturing, healthcare, and has led research programs examining the implication of new technologies in rail, highways, and aviation. She was the president of the Chartered Institute of Ergonomics and Human Factors in 2015. Through to 2016, and was elected as Fellow of the Royal Academy of Engineering in 2024. So I'd like you to join me in welcoming Sarah to give us our lecture tonight.
Thank you very much. It's a real honour to see so many familiar faces in the audience. It's also slightly terrifying to see so many familiar faces in the audience, because I know how much more about this topic you know than I do. But I'd really like to thank Carolyn, first of all, for the invitation, but also the provocation, because I think that there's a real need for action, for us to think about how we can really effectively bring the knowledge of human factors, the discipline of engineering together to address the opportunities and challenges we see around automation and autonomous systems. On the 8th of January 1989, British Midlands Flight 092 crashed into the embankment at the side of the M1 just before its target destination of East Midlands Airport, just a few miles from where I now live in Nottingham. Of the 126 people aboard, 47 died and 74 sustained serious injuries. The aircraft had suffered a mechanical failure in one of its engines. However, the pilots mistakenly shut down the good, functioning engine rather than the one which had failed. Many lessons were learned from this tragic incident. In particular, human factors analysis showed that there were many reasons why the pilots believed that they had shut down the correct engine. These factors related to the way the cockpit displays were designed, their understanding of the reliability of different instruments in the cockpit, the number of interruptions and alarms that impacted on the pilot's ability to step back and analyse their actions, and their own mental models of how some of the elements of the aircraft operated. It was after a lecture, which included a video about this incident, that I, then a psychology undergraduate, first learned about the discipline of ergonomics and human factors. We use the terms synonymously in the UK. And I was inspired to move into a world of engineering, systems thinking, and human-centred design. And I was inspired to spend over 30 years thinking about how humans and technology can work together in partnership. Now, one of the ways that many of you will have heard me explain human factors to non-specialists is that humans are fallible and humans are brilliant. Our job is to minimise the impact of human fallibility and maximise the value of human brilliance. It can be easy to think of examples of human fallibility. The human body and mind have characteristics that make them susceptible to everything from physical fatigue to cognitive distraction. But people are brilliant too. A notable example of human brilliance was seen on January the 15th, 2009. An Airbus A320 struck a flock of birds shortly after takeoff from LaGuardia Airport in New York, losing all engine power. Given their position in relation to the available airports and their low altitude, pilots Chesley Sully Sonnenberger and Jeffrey Skiles decided to glide the plane to ditching on the Hudson River. All 155 people on board survived. The time from the bird strike to the ditching was less than 4 minutes. But in fact, we're surrounded by human brilliance like this, and most instances of human brilliance do not make the news. That moment where we slow down on approach to a pedestrian crossing as we notice the group of small children who are looking rather excitable and we aren't quite sure whether or not they're going to step out into the road. That person who we all know, who has worked for years with a particular engineering machine, who knows all of its foibles and can tell just by listening whether a little bit of maintenance is needed or not. Or that person who's been trained to look out for signs of suicidal behaviour and has the confidence to go over to a person and start speaking to them. Both the Kegworth pilots and Sully thought they were doing the right thing. They were experienced. They recognised their responsibility. They acted in a way that they believed was best for the safety of their aircraft and their passengers. We are in an era where systems are being dramatically changed by automation. Automation is not new, but its impact is rapidly becoming visible and impactful in roles where we have not previously seen it. Nottingham is not just famous for Thomas Hawksley. Automation has been replacing physical activities for humans for centuries, since the days of the Luddites, who in 1812 smashed up their knitting frames in protest at the threat to their manual work of manufacturing stockings in that same Nottingham. But automation is now starting to replace more and more cognitive elements of our work, particularly, as Carolyn has said, through the increased adoption of artificial intelligence. Now, the beauty of human action, the source of that brilliance, is in the complexity of how the human processes of decision-making, analysis, and action work. But this complexity presents a challenge when it comes to assuring the safety of systems where the human is a significant actor. And automation is blurring the boundaries between the responsibilities and actions of the human and the technology with which they work. No longer is it clear or simple to allocate responsibility for elements of a task neatly to either the human or the engineered system. Very often there is seamless partnership between the two, meaning that the optimal performance of both elements is dependent on that of each other. But we still need to provide advice and evidence to demonstrate and assure the safety of these complex systems, the technological and the engineered elements, as well as the human. And whilst this is not a new challenge, it's one that's increasing in complexity and is becoming increasingly relevant in a number of contexts. There are so many examples that I see in my everyday work of where it will be highly beneficial to have people and automation working in partnership. For example, the use of artificial intelligence to help select alternative flight levels during a plane journey to reduce and avoid exposure to supersaturated areas of the atmosphere, thus mitigating the production of contrails and associated net warming effects. Or an office-based operator supporting the deployment of autonomous trucks delivering freight. The underground station manager monitoring crowd movements in a busy station during rush hour, supported by the advice from a system that predicts passenger volumes. Or a ship's pilot who's maintaining situation awareness while having the navigation of their vessel supported by sensor systems and automation. Or the car driver who's supported by computer vision, interpreting the signs at the side of the road, is reminded via an auditory warning that they are exceeding the speed limit. For each of these examples and many, many more, automation is taking responsibility for much of the task, but the human still retains a role and a certain level of accountability. We're introducing technologies because we believe that they can do a task better or faster than a person, but we're asking the person to retain responsibility. This is one of the ironies of automation identified by Liz M. Bainbridge in her brilliant 1983 paper. How do we assure, therefore, the safety of different elements of this system, and how do we assure the system as a whole? So I've been asked to speak to you today to start the conversation about how we tackle this challenge. How do we maintain the value of human brilliance? How do we ensure that we continue to design jobs and tasks that are rewarding, engaging, responsible, but have appropriate safety assurances. Now, I need to apologise because I am not going to come up with some sort of magic solution. And there are many of you here who know more about this topic than I do. But I hope that we can start to set a framework that we can all work from to think about how we can take the best of our traditional, robust and reliable approaches to safety assurance of physical and digital systems. How we can learn from work that's been done to manage safety of complex systems involving people, and how we can prioritise our actions for the future. So let's step back and think about how we do this at the moment. We have a strong and proud history of testing and defining safety requirements for engineered components of complex systems. We can use increasingly sophisticated methods to measure and test the tolerances of different materials. We can define safety parameters that represent a range of different scenarios, and we can have high level of confidences that our comprehensive testing can inform decision-making. I'm going to give you an example of something we've been discussing in the Department for Transport with our Transport Research and Innovation Board over the past few weeks. Transport infrastructure delivery partners have identified an opportunity to increase the adoption of calcined clay for low-carbon concrete, potentially reducing carbon emissions by 70% and reducing costs by 30%. The team have done a great job at looking at the business context and the environmental benefits. Now, I am not an expert in calcined clay, so I asked for further information about the evidence for the performance so that I could make sure that any advice that we gave was taking into account that this environmentally preferable solution would not compromise safety. In response to this request, I received an excellent summary note. It referred to a British standard that defined compliance considerations, and it reported analysis of various durability parameters, carbonation, chloride ingress, freeze-thaw, and thermal properties. On the basis of that evidence and the expertise of the person who provided it, I was comfortable we could advise the department that this was an environmentally friendly solution that would deliver appropriate levels of performance in certain circumstances. And we've seen examples where these methods have been applied to digital systems. You can see example on the slide of some work that's been led by John McDermott and colleagues at the University of York. They've developed the AMLAS method to assure machine learning using this type of approach for use in systems. So what's the equivalent for human elements in a complex system? And how would that conversation have gone, that conversation about calcined clay, if what we'd been considering and advising on was a human technology cooperative system? Within the world of ergonomics, we are blessed with many, many examples of methods that have helped us evaluate the suitability of physical settings for people. Building on tools from the 1980s, such as rapid upper limb assessment and SAMI, and on the basis of really robust evidence about the long and short-term physiological implications of different work activities, we've been able to inform the development of three-dimensional models of work environments, informed by a range of different anthropometric data sets to evaluate the physical risks associated with work and make sure we mitigate them. These are now routinely used in many engineering design processes. We also have increasingly advanced sensing and tracking technologies. Watch this person's nose. And we're starting to learn more about human behaviour and responses. We can track the movements of crowds in settings. We can learn from patterns of behaviour in different circumstances and times. We can collect information from planes, boats, trains and cars to learn how pilots and drivers have performed in different types of situations. Here we see an example of facial thermography. The nose area became colder as work demand rapidly increased, and we're seeing these types of technologies increasingly being used in work and control settings. As well as theories about physical work, we also have theories about cognitive work. They help us to predict the way that people will be able to cope in complex environments. They help us to predict the impact of changes, particularly in highlighting the known risks of underload, not enough demand, and overload, too much demand. And we've got many, many methods, such as the operational demand evaluation checklist, that have been developed to provide a quantitative view of the different types of factors that influence the extent to which an individual or a team are able to cope with demands placed upon them. And we're able to predict the impact of human reliability on a system. This feels a bit like that calcined clay example. But they still require expert judgment to apply and interpret the results. And they are still critically very much influenced by the specific context. As Carolyn mentioned, we have a long history in the use of simulation and testing to assure human performance. Pilots, train and tram drivers, you may notice that is not a real tram driver, now routinely have their driving or flying performance assessments in real-world settings supplemented by simulation tests. And of course, many of us may well have had our own control of an automobile assessed by taking a driving test. But very often, these tests still rely, to some extent, on the expertise or judgment of a human expert assessor. Now, this not only leaves a small window of ambiguity or subjectivity, although the expertise amongst those assessors is very, very high. But more importantly, it limits capacity due to the limited availability of these experts. To put that into context, there are around 2,000 members of the Chartered Institute of Ergonomics and Human Factors, around 800 registered and chartered professionals. So we don't have many of these experts to help lean into all of these processes. Now, I was recently on a visit to Dubai for the Intelligent Transport Systems World Congress. And one of the many things I learned about there was the approach being taken to driving tests in Abu Dhabi. Here, all driving tests are conducted using a highly instrumented vehicle. The movement of the vehicle and the activities of the driver are sensed and monitored. And at the end of the test, there's a printout, it's quite nice there's a printout, from a computer in the back of the vehicle, which explains to the candidate whether or not they have passed or failed. There is someone else in the vehicle, but they're a safety driver, ready to intervene on the brake in an emergency, rather than an expert driving examiner. Now, a method like this still needs a real-world setting, or at least a very, very sophisticated simulation of one. But what methods do we have that can anticipate future settings or use metrics like that analysis of calcined clay? I saw a great example of this in a conversation we were having recently in the department about some of the challenges that we were discussing. We've got a new commitment to really thinking about transport in an integrated way. And we know that when we develop integrated transport systems, we need to consider accessibility in elements of design guidance. Now, we already have an excellent set of what are called transport user personas developed from within the Department for Transport. One of my colleagues asked, well, how can we use these perhaps to expand them, to represent a range of different user types, user needs, user scenarios, and maybe we go to different elements of the transport system, different places in the UK, and evaluate how many of which different types of travellers are supported or not by our current designs, and what would we need to change to our designs to make them increasingly supported. You can see that we can start to use this type of approach to develop some metrics so that we can perhaps at least compare different solutions on the basis of their inclusivity. But none of this really gets to the nub of the issue, which is the complexity of safety. Safety is not a moment in time or a state. It's an emergent property of a complex system. And we need to remember that even structured engineering and simulation tests are not perfect. The original cause of that Kegworth M1 crash was aerodynamic flutter, which caused the engine to fail. And it was found that the testing programme didn't take into account the full characteristics of the life cycle of the component. In the VW Dieselgate scandal that my predecessor at the department was very involved in advising on, it became apparent that the testing scenario for the selective catalytic reduction could be gamed, and that real-world performance did not reflect testing results. And automated and autonomous technologies complicate things even more. No longer is the notion of tasks or goals, those motivational factors, they're no longer the sole preserves of people in our complex systems. We can start to see situations in which technologies have purpose, technologies have goals, technologies have emotions, to learn, to evolve, to survive. So how can we take testing approaches that support different elements of a system, human and engineered, into the complex context of safety for automated and autonomous technologies? Now, someone who's really internationally led thought around this is Nancy Leveson from MIT. And in 2009, she published a really helpful white paper that talked about different approaches to safety. The approaches highlight different aspects of a complex system which contribute to its overall safety. The presence of redundancy within a design system, evidence of continued testing and refining of the performance of the system as a whole, and the application of hazard analysis to ensure there's been a process of stepping back and thinking about the vulnerabilities within the system and the appropriate mitigations. She also highlights the really important difference between reliability engineering and safety. In some instances, increasing reliability can actually have a negative effect on safety. For example, increasing the pressure in a combined system could lead to better system performance, but could result in a greater consequence if there were to be a failure. It's also often the case that reliability failure does not have a safety consequence, and often as a result of human action to compensate or redundancy within the system. So since the formation 75 years ago of what's now the Chartered Institute for Ergonomics and Human Factors, there's been an increased capability in understanding of the role of the human in a complex system. This has led to an increase in the visibility and the recognition of the importance of understanding of how people interact with technologies and their settings. But human factors can still be seen as a siloed activity, a nice to have, an afterthought. At the heart of ergonomics and human factors is systems thinking. Now, I know there are other human factors and ergonomics specialists in the room. I don't think, when you're trained as a human factors and ergonomics specialists, we're ever sat down and explicitly taught how to think in systems. I certainly don't remember that happening. It's just inherent to all that we do. And systems thinking is critical to safety. Systems safety emphasises building in safety at the outset, not adding it on to a completed design or thinking about it late in the design process. Systems safety deals with systems as a whole, rather than with subsystems or components. Safety is an emergent property of systems, not a component property. Systems safety takes a larger view of hazards than just failures. Hazards are not always caused by failures, not all failures cause hazards. And it emphasises analysis rather than past experience and standards. And it emphasises qualitative rather than quantitative approaches. It explicitly recognises trade-offs. We had a brilliant example of trade-offs in DFT just last week, a goal of biodiversity to increase wildlife in an area potentially increasing risks of bird strikes for aircraft, for example. Systems safety is more than systems engineering. Systems safety engineering is an important part of systems safety, but the concerns of systems safety extend beyond the traditional bounds of engineering. Why is this? People bring complexity. The very thing that results in human brilliance, the actions of Sully, are the same things that means it can be very difficult, foolish even, to claim we will ever be able to predict all of the ways in which a human will act or perform in a complex system. And I would argue, in fact, we don't want to, because without human brilliance, we won't have new discoveries, we won't have inventions. In some cases, we've got really great data about complexity and variability. We've got comprehensive sets of data about human physical characteristics. We've got models about how we process information. We've got a really good understanding of how the human visual and auditory systems work. But we still need to pull all of these elements together. We need to understand the performance of a system. And we need to recognise that individuals, like engineering components, do not respond independently. We can't make that assumption of independence if we recognise that people are social beings. This means that when we calculate the probability of events, there are going to be complex interactions that play out differently on different parts of a system. Now, human factors professionals have been tackling this challenge of complexity for many years. Methods such as cognitive work analysis, FRAM, functional resonance analysis method, as you see here, and AXIMAPS have emerged to help us make sense of complexity, to identify the interplay between different elements of the complex system. But I've heard views from non-specialists that whilst recognising that these methods do represent that complexity effectively, they don't do enough to actually help know what an individual actor should actually do. Very often, individuals in engineering projects are responsible for just a small part of the complex system. And for those individuals, having a complex system model like this is just frustrating. I heard a colleague say something along the lines of, if someone shows me another diagram with a load of boxes and arrows, I will scream. And this wasn't due to a lack of willingness to help or a lack of engagement. It was a voiced frustration that simply saying it's complicated does not always support the identification of a solution. We've also seen a recognition that it's not simply appropriate to evaluate or assure a product, an end state of a system, but we also need to assure or influence the process. So we need to understand whether there's a positive safety culture in an organisation, whether there's an appropriate safety management system in place, how performance of the system as a whole is monitored, whether near misses are given attention, whether they ensure learning from when things went right as well as when things went wrong. And industries such as air traffic control have been international leaders in taking this holistic approach to assurance and continuous improvement of safety in systems. The increasing presence of automation in complex systems is necessitating the consideration of these types of assurance activities in a wider range of settings. Increased automation in vehicles means they can no longer be tested through engineering assessments alone. Automation is supporting everything from decision-making in port logistics to management of multimodal transport interchanges. Full automation, where the technology is fully taking on the responsibility of actions as part of a system from a person, is being certified through complex testing, often through a wide range of scenarios to try to replicate the real world. But where it becomes particularly challenging are where people are working with technology in partnership, where the responsibility and the accountability still remains with the person, as we currently see with driving technologies, but where there is collaboration between people and technologies. So the exam question I frequently pose is, how can we ensure we're being reasonable in holding the person responsible for the state of a complex system? The challenges of automation in design of complex systems are well rehearsed. We know we tend to automate the things which are easy to automate, leading to a potpourri of leftover automation. We ask people to take responsibility for the outputs of technology that has been introduced for the very purpose of doing the job faster or more accurately. And we know that replacing people can lead to a loss of skills and a loss of understanding of how a complete system works, which can result in them becoming out of loop. We also see challenges for human operators. We see lack of consistency in the design of technologies like these infusion devices. That means that sometimes technologies that do the same thing look different and require different types of interaction. There's no consistency in display or interaction between different manufacturing systems. But we also know that we sometimes have different technologies that look the same but behave differently. And in fact, in the Kegworth incident, there was a vibration gauge that gave information that showed the wrong engine had been shut down. It had been previously known to be unreliable, but in a recent upgrade, it had improved and its reliability was in fact high. For whatever reason, either the high demand of the emergency situation or the brief nature of the training that had highlighted this change, the pilots did not take this information into account when they were reviewing their decision-making during the emergency. And we know that many types of automation, and AI in particular, is only as good as the data on which it's tested. We see this bias playing out with technologies that are not equally able to be used by people of different ethnicity, or in edge cases which haven't been modelled or predicted in technologies such as autonomous vehicles. So how do we take the positives of automation into complex systems? How do we responsibly ensure the person's able to take responsibility for some elements, but in others, make sure the responsibility lays with the technology? How can we assure the safety of systems where people may be involved, but where their actions may be unpredictable? How do we minimise the impact of human fallibility and maximise the value of human brilliance? And how do we avoid ergonomists and human factor specialists being the cautious plumbers of the future complex systems? That risk that our view is this is just complicated. So I think there's a couple of things we are doing and we can do. We can have embedded human factors experts in industrial settings. We know of examples where this has made an enormous difference. Some of you represent those people. The work of Anne Mills in rail, Laura Pickup in healthcare, Nick Reed in driving, Steve Shorrock in air traffic control are a few examples of this approach. But this isn't scalable. Ergonomists as brilliant as Anne, Laura, Nick and Steve are sadly not in all settings where people and technology are working together. So we also need to develop methods which are usable by non-human factors experts. Now, these methods won't give as much as an expert assessment would, but they can be helpful, and more importantly, they can help to identify when specialist advice is potentially needed. I knew I didn't know about calcined clay, so I knew I had to ask that question. How do we make sure that happens in the opposite situation? There are some of these tools, but not enough. There are some examples where we publish human factors information through, for example, Skybree and Spark that are supported by Eurocontrol and Rail Safety and Standards Board. But these often fall into the category of advice and can really quickly become overwhelming, especially for non-human factors experts. I strongly agree with Carolyn that multidisciplinary teams are key. We all know it's unhelpful if we end up with one profession preaching to or arguing with another. So the involvement of human factors experts in standards committees, nationally and internationally, is a really important thing we need to pursue. But we need to make sure that all those involved in safety assurance know what they do not know. An example that I'm really impressed with is the Engineers 2030 work that's being led by the Royal Academy of Engineering. This recognises the importance of multidisciplinary thinking and highlights systems thinking and human-centred design. So I'm going to end with a call to action. I think there are things we can all do, no matter what role we play, in advising, assuring, designing, using or testing complex systems. I can start by coming up with some starting points, but it's clear to me that where we are now is not where we need to be in the future. I think we can all share and make visible usable methods for non-experts. We can provide clear guidance to help people assess human-involving safety issues where appropriate, but give them confidence to know when they're able to make the assessment and when they need expert advice. We can build multidisciplinary communities of practice. I know of a great example where the human factors leads of the accident investigation boards all get together. But what can we do to encourage communities like that which are multidisciplinary? And maybe, rather than communities of practice, we need communities of challenge and communities of learning. Whilst we can challenge ourselves to think about what we can measure quantitatively, we do also need to preserve that qualitative understanding of the true nature of a complex system. And where that qualitative understanding is needed, we need to think about tools to make qualitative data accessible and usable, for example, through careful application of AI tools to interpret natural language. We can have events like this that build understanding of different disciplines. I'm a big fan of pairing schemes, and I've seen a really positive impact of them. Maybe one of the outcomes of today's discussion could be to think about pairing schemes that specifically tackle this challenge. And we can continue to work on the use of simulation and testing, particularly where we can build large and varied sets of scenarios that include qualitative, social, and collective elements as well as quantitative. And we can ensure that as we're introducing increasing automation into complex workplaces, we do not assume that if a technology is assured at the outset, our job is done. Technology will evolve. How technology is used is key. So therefore, we need intelligent in-use monitoring, appropriate methods of data collection, and more importantly, a culture of continuous learning, reflection, and sharing of data with a common mission to deliver safe systems. But all of these ideas are about process, and I'm not sure that's quite enough. It doesn't quite respond to Carolyn's challenge. We need to recognise that the world has changed. Human technology cooperative systems are here to stay. With people involved, we are not going to get the predictability, the exhaustive nature of testing of engineered systems. How can we come up with guidance and principles based on that 75 years of theory we've developed in human factors? Principles like redundancy, usability, reflection, monitoring, social, and challenge. So I'd sum all of this up as being a mission towards responsible automation. Automation that makes systems safer, automation that makes people safer, and automation that makes the world safer. Thank you, and I really look forward to the panel discussion. Thank you.
So, there you go. Thought-provoking, to say the least. Thank you very much, Sarah. Your job is not yet done. Sarah's joining our panel, and we will be coming back to the challenge that Sarah's left with her last slide at the end of the evening. But thank you very much, Sarah. It's absolutely fascinating. It's my great pleasure now to introduce the chair of the panel discussion, who is Paul Campion. Paul is the Chief Executive Officer for the Transport Research Laboratory. So absolutely fitting for this evening to conduct our discussion following Sarah's lecture. Previously, Paul was the Transport System Catapult, working for the Transport System Catapult, and his forte is working in innovation and change. So again, absolutely aligning with what we're thinking about this evening. So Paul, can I welcome you to the stage, and Paul will introduce the other panel members. Thank you very much, Paul.
Thank you, Karen. Good evening, everyone. I'll get my excuse in early. I'm late stand-in for Richard Courden, who works for 2L, who is a genuine expert in this area. I'm a genuine not expert in this area. But I am extraordinarily privileged to have a fantastic set of speakers, and my goodness, what a extraordinary, provocation and speech. I look forward to the 12-part television series that expands on that. So much content was there. Heaven knows how we're going to get it done in half an hour. Can I suggest the panel members come up, please, and as you're doing that, no, just come up. I will do a brief introduction for you, because we've only really got half an hour. So what we're going to try and do is, in half an hour, cover some of the issues that Carolyn and particularly Sarah have raised. Clearly, in half an hour, impossible to do all of that justice. So I'm going to fire off some questions, and I hope we'll try and reserve a little bit of the time for your questions, but it's a short amount of time. So, a fantastic panel, I think in this order. So Professor Mark Young, who is at the University of Southampton, is Professor of Human Factors, and he's the current President of the Chartered Institute of Ergonomics and Human Factors. Claire Pollard, who's from AWE, so from the nuclear industry, Human Factors Lead Technical Authority. There's an industry that we want to be super safe, don't we? So the way that all of the disciplines involved in that industry come together safely is Claire's specialism. Chris Knowles is Director of System Safety and Health at the RSSB, so the Rail Standards and Safety Board. I'll come back to that one in just a second. Professor Patrick Baker is a head of science for Royal Air Force. He said I should call him a mad scientist. Well, he's certainly a scientist. Among his responsibilities are intelligent machines for the Royal Air Force, and he's a visiting professor at Loughborough. We will judge for ourselves whether he's mad. I think what we've got is a very broad set of representatives from industries which, with the grateful exception perhaps of the nuclear industry, have all been on safety journeys, have they not? And anyone who's got any interest in transport knows that pretty much every transport mode started as an extraordinarily effective killing machine. Certainly true for rail, for the road, for air, and they have all over time found ways to be safer, not to say the job's done. But as Sarah illustrated, we've got a whole different set of technologies coming in now which are going to make the job, I think, potentially much more difficult. It's very tempting, isn't it, to think of the Luddites and think they had a good idea going. Is this really worth doing? This sounds really, really hard. What are the benefits that justify all this hard work? Now, Sarah, you gave 5 or 6 examples, so forgive me, I'm going to skip over you, and I'm going to, for this one at least, and I'm going to ask each of the other panel members to have a go. Is it really worth all this hassle? Why would we go to automation? Can I start with you, Mark, and then we'll go down the road.
Thank you. Well, I think the answer's got to be yes. We would risk putting ourselves, I think Sarah's made the point in her lecture, that as human factors professionals, we're always uber cautious about implementing technologies like this, implementing them around the user, making sure that everything is fit for purpose, fit for human use. But we're not Luddites. We risk coming across as technophobic, and that is absolutely not the case. We would not wish to stop the tide of technology, nor can we, I don't think. It's about doing it in the right way. It's about putting the human at the centre of all of that. All the time that we need a human in that automated system, which I think will be the case for some time yet in many transport domains and elsewhere, we need to understand their capabilities, their limitations, and build the system around those. People don't cause accidents most of the time. They just don't stop them. They are the end of a complex series of factors that leads up to that point in the chain of events. And they've been given a situation more often than not by a system, maybe an automated driving system, that's thrown up its hands and said, can you take over now because I can't do this? And that's not an ideal situation to put a human into. So we need to understand the situation, the context, the decisions that that person needs to make, and build the system around them.
Okay, you gave me a strong yes and then several reasons why I should be careful about it. Claire.
I think I agree with everything that Mark said, apart from the Luddite thing. But I think from my perspective from the nuclear industry, the most important thing is protecting the people, of course, and any opportunity to remove the people from the immediate area where the hazard is and move to remote operations has to be the most important thing for us. Protecting our people is the most important thing. But we need to understand what the failure modes are, what failure looks like, and how we predict that for defining risk, and writing our safety cases is going to become really important. And is going to absolutely change how we do our work.
I'm sure we'll come back to this point about safety cases, but let me just pass on, Chris, to you.
Well, thank you. Well, I equally am not a human factor specialist. I'm an asset manager, engineer and asset manager by background. So
we're going to have to stick together then.
Indeed. So from an asset manager's point of view, you're always aiming to drive out value. And by that I mean get value from your asset base, get value from the things that you are doing. And I think in the sense of automation, it's a sense of knowing why you want to do it. What is the value that you want from the automation? What are the opportunities, essentially, that you are seizing through going down the path of automation? Is it about consistency? Is it about helping people deal with a workload issue? Is it about support to decisions that they are making? And I use the word support there as a sort of a semi-automation piece rather than taking over that decision from the human entirely. So do it because it helps. Do it because it brings value. Don't do it because we can. I think there are aspects around assurance as well, but we might come to that later.
Okay. And finally, Patrick.
Interestingly, one of my colleagues survived the Kegworth air crash and was upside down in a seat for 2 hours before he was rescued, which was obviously what it is. I work in defence, so we try and move at machine speed, unfortunately. The adversary tries it, we try it. So the level of information that we're now trying to deal with, second by second, is so vast. We have no hope of the human dealing with it, to be honest with you. And you can see that built into the aircraft. If you look at the Second World War, let's say a strategic bomber would have a crew of 8. By the 1960s, we kind of brought that down to 2. The same in civil aviation. You used to get a crew of 3 or 4 or 5 in the flight deck. It's now 2. Is it going to be 1? And is it going to be none? Is the question. I think automation is just a natural progression. It's a bit like AI. Do we trust it? Probably not. Will we trust it? Much in the same way 20 years or 30 years ago, did you trust, if you bought a new car, you got a book that came with the car that said dip the oil and check the tyres before you drive it. I bet you don't anymore. You trust the car to sense it for you. So I think we're already on that path and we just need to embrace it. Where the human fits in that, as far as in defence and aviation is concerned, that is the point of, let's be honest with you, responsibility.
Okay.
Thank you.
Very good, thank you. Well, forgive me if I cut you off there, Patrick, but we've got a very short time and I'll make sure everyone gets a thing. So let me, rather than then going back over all the reasons why it's hard, because I think, Sarah, in particular, you articulated that extremely well. I want to drill down perhaps to one aspect of that, which very loosely is the ethical aspect. And I'm picking up on the word responsibility here. You talked about, who's responsible in a complex human, particularly AI situation. Patrick, you just mentioned the same, so we've already touched on it. How can we think about this differently? This feels to me as much a social problem as an engineering problem. And I could imagine that a lot of problems which currently can be addressed in the final analysis by, as it were, the criminal law, can't be touched in that way. This is a society acceptance rather than a human acceptance point. And maybe you feel that's out of scope for engineers. But I think that the society will probably want to pin it on the engineers. So maybe we should think about it first. Sarah,
I think there are two separate issues, actually. So I think that very much for all of us involved in implementing and designing new engineering systems, we do need to think about societal acceptance of those technologies. And ethical considerations of just responsible innovation generally. And I do think that's a matter for engineers and technologists and anyone involved in those sorts of situations. However, I think that is a different issue to whether it is reasonable to hold a person responsible for the actions of either a whole system or components within a system. I'll give you an example from the world of automated vehicles. We're seeing the Automated Vehicles Act, which has a really clear legislative framework that provides a very strong framework for accountability for full automated vehicles with the notion of an authorised self-driving entity. So you've got a complete change in the legislative framework. What we are starting to see, though, is increasing levels of automation within vehicles. And that's where the lines start to become blurred. Because we start to see issues such as underload, out of loop, where, in my view, we will get to a point where it no longer is reasonable to recognise that a person is able to respond quickly. Mark articulated it really well. The user ends up being the recipient of lots of other things that have happened within the system. And I think coming up with appropriate methods that allow us to identify when it, frankly, just becomes unreasonable to expect the person to respond in an appropriate way is something that we do need to work collectively towards.
So you incline to the view that SAE level 3 doesn't even exist?
I'm not going to be drawn on SAE levels here because that's a whole other lecture. But I think there needs to be clear water between the point at which we have automation that helps the driver drive more effectively and that very clear perspective where we have full automation. I will remind everyone at this point, I don't speak for the Department for Transport. I am an advisor to the Department for Transport.
We're suddenly going to go confidential here, so you can stop recording. Mark, forgive me if this is unfair, but from a university, from inside academia, do you feel that this topic is being addressed at all, or are we focusing on the process, I think was the phrase that Sarah used, on the technicalities rather than the implications of this change?
No, I think it is being addressed. Caroline, I think, made the point earlier, there's a ton of research going on in academia on these very topics, and it's a case then of actually getting that integrated into the applied world and picked up by people like this, the engineers of the world who are implementing these systems. And I think the point earlier you're making about the ethics and the responsibility around this is 100% within the scope of engineers, because it's about how you design and engineer these systems, I'll say it again, around the human. Where those lines of responsibility lie, as Sarah's just pointed out, is crucial as we transition from a world from level 2 into level 3. What I think of as the difficult adolescence of automated of levels of automation. We need to be absolutely crystal clear with those drivers who is in control and what they are doing. I think about it as a team working issue, actually. They are systems approach, they are members of the same team in that system, and we should treat them as such. And we should actually design systems from a team working perspective around principles of cooperation, communication, coordination, put those into design principles, because what that system says to the driver via interfaces, via bells and whistles, alarms and alerts, actually tells that person, I'm doing this now, you can do that bit, rather than sitting there silently and saying, I'm okay here, until I'm not, and then, oh, by the way, it's all over to you now. And I think another part of that, if I could make the last point, is a very simple one to some extent. It's just how we label these systems as well, because calling systems things like autopilot is perhaps not very helpful when in the small print of the manual, you know that system will say, you're in control here, by the way, and who actually reads that manual anyway?
So that's a very deep design question about how the two elements of the system work together. Whereas at the moment, perhaps we've got a rather facile view, which is either them or us.
Indeed.
Claire, if you don't mind me picking up on that, following up on that point, you were describing your role inside AWE very much as bringing together all the various technical disciplines in order to ensure that they work together in a way to deliver the system. So as the content becomes less deterministic, as we start maybe to have to think about artificial intelligence and natural intelligence as two varieties of sort of the same thing, how does that job change?
Well, we need to understand what that is going to mean for operators, maintainers, engineers. We're still going to have to place claims, safety claims on people. So what that means from the operator's perspective, I don't know, because I don't know what it looks like yet. But currently, you know, there tends to be a driver to automate things that are easy to automate and get the operators to do the bit left over. But always be in control, always be responsible for what's happening. But we do need to think about where our levels of risk, what levels of risk we're happy to accept, and really, you know, what that looks like in terms of the design of the operator's tasks and how we keep them in the loop of what is happening is going to be really important. I don't think it's a novel question. It goes back to automation as we've understood it for years. It's just now with what autonomous systems look like and what they're going to look like in the future, that does become more complex. But what that means in terms of where the safety claims are is up for discussion, I think. I don't think I can answer that question.
No, that's very... Well, I mean, if you knew the answer, I'd been amazed, by the way. It was an unfair question. Chris, if you don't mind me saying so, the rail industry perhaps is more conservative than some of the other elements of the transport thing, for very good safety-related reasons. I could imagine that the system could struggle to adopt automation in any really serious way for precisely that reason. Does that mean the benefits we talk about are not going to be acceptable? Can the rail industry take responsibility for maybe not having complete control?
An enormous question. There's a lot in there. The railways, in the sense of automation, there's levels of automation already in place. I mean, if you looked at the Docklands Light Railway, for example, as one, if you step onto one of the trains on the Docklands Light Railway, you're not going to see a driver, for example. So, and people have accepted.
No, it's not true. I'll be at the front driving.
Indeed, you get that driver's side view. I think there are a number of things here across the automation. Are the railways conservative? Yes, potentially. But we've also learned a lot from operational experience. You know, I was looking at the portrait on the wall there. I think of the first president. I think of the IMechE first day of the operation of the Liverpool-Manchester Railway.
Didn't go well, did it? Didn't go well. An MP was killed, you know, arguably the first railway accident. But we have always learned from those things, and we have built up a lot of experience in how we build those lessons into safety assurance, how we make sure that we're considering those factors, understanding the hazards at the outset when we're looking at a system, and that includes the way that the operators, the maintainers, will interact with those systems, and then looking at the way we would design and assure things accordingly. We did a piece of research relatively recently looking at how we would carry out assurance of signalling systems that might be 15 years away, 20 years away. And the review was really looking at how would we consider the effectiveness of current assurance techniques if we're applying them to those types of systems in the future. And this was a point of a presentation we gave at PACTS, also just to give some of that feedback. Now, we didn't come to full conclusions. We generated an awful lot more questions, but there were a few things that did come out. Artificial intelligence, machine learning systems were certainly part of that, and we were looking at their application in safety-critical applications. That research came to the recommendation that actually today, something that was safety-critical, I'm using that term loosely because there are different levels of that, but you wouldn't comfortably put artificial intelligence into that safety-critical position today with current assurance techniques. That said, absolutely we have to grasp those opportunities and develop those assurance techniques so we can seize the opportunities, so we do end up with the improved
functionality and safety that will come from that. We will need to understand that we have sufficient confidence with the wraparound in those systems that we've got those controls in place, and we've demonstrated safety so far as is reasonably practicable. One last point I would add as well, I think, where we are using automation, it's making sure we're considering the human behaviours in using those automated systems. Decision support, for example, where you are suggesting certain things from the use of machine learning-based systems to actually inform engineers and railway operators about safe operating practice. There is a system that we are piloting at the moment in this space. It's making sure that that is decision support. It will be in a position where it's giving tremendously good advice. We don't necessarily want that to drift into complete trust in that system, that's saying the human is now just relying on that and ignoring the other context that they may be aware of.
That last point is a really fascinating. I'll throw that straight over to Patrick, because the Boeing Aircraft Company has suffered recently, has it not, from getting that decision point completely wrong. I mean, aviation's got a very strong record in incorporating automation safely, and then this. What went wrong?
Thinking about that, think of it maybe another way. This is human-centric. We still use humans everywhere in defence to make decisions. If we think along the lines, potentially the human could have saved the day. So, for example, on the Kegworth one, had the pilots, I know it was dark, fell back to what they should have done, which is which foot on which rudder pedal is down, would have told you which engine wasn't working pretty quickly on a twin-engine aeroplane. That's uniform for all twin-engine aeroplanes. So some of the skills that we've got as humans, automation is actually doing those in, to be honest with you. Slowly, they are disappearing. We begin to trust the system. You begin to trust the system implicitly. At what point does that become a huge problem to you? So there is a danger here that automation can help the human to achieve greater things, but also stop the human from achieving greater things. And I think that's a concern. That's something we've been looking into for quite some time. I work with some extremely qualified test pilots who I fly with, and they go, oh, by the way, did you feel that slight flutter? I've got no idea what they're on about. It means nothing to me. But their experience is telling them that. I can tell you the sensors on the airplane, we do operate on behalf of the National Digital Twin Programme, an airplane which we're digitally twinning, because that seems to be the vogue at the moment. Happy days. And don't worry, we've done it all ethically, because I had to do an ethical case around it. Same as all our AI is ethical. Somebody has an interesting one for you. Automation and AI. A couple of years ago, the head of NORAD asked me, he said, Patrick, is AI going to start an unethical arms race? There's an interesting point. Can you guess what I responded with? When was the last time we had an ethical arms race?
So, we'll talk about that one later, that's sure. Right. One more question from me, and then we'll see whether we've got any questions from the audience. It's extraordinary how tight. No, we haven't? No time? No questions at all. Right. Last question. This is a whole new world. How do we train tomorrow's engineers, and what do we do about today's engineers to enable them and us to cope with this world? I'm going to go this direction, so Sarah gets the last word. So Patrick.
Well, interestingly, I do a lot of work with a lot of US academia, and I did a lot of work on distributed machine learning models. This is kind of where you distribute them out in the field. They all go and learn stuff. Then they all know different stuff, which in my world is really quite dangerous, because they all know something different, so you have to flatten them out. And weirdly, I kind of took a long look at it and decided that we're using the wrong people to work on this. The last thing we want is a bunch of computer scientists to do this. So I brought in a 24-year-old biology grad to take a look at it, who looked at it for about 3 or 4 months and came up with a solution that I'd never thought of. So potentially, from an engineering perspective, this is an opportunity to really employ diversity of thought. And that's really important. And bake that in from day one. You know, potentially, partially rip the rule book up. Try and bring people in who are slightly different. For example, I do AI development with a 25-year-old RAF policeman. Why not?
Yeah, why not? So is the rail industry ready for interpretive dance as a as a new way of working?
I won't answer the question using interpretive dance.
Oh.
No.
It was right there for you. You could have.
If I give one anecdote, the advice from my father when I was starting out in my career was study engineering, qualify as an accountant, and then do neither, which I think was ultimately a route into asset management for me. But the observation I have from that, I did study engineering, qualified as an engineer, but I also studied finance, but to the level where I could talk to and engage with the accountants, because you can't build anything without the money and the understanding of the business cases and so on. But when I look back on my formative training, there was nothing around human factors. Actually, in the academic training that we had, there was nothing around assurance. These are, I have a small appreciation of human factors now. I've a good appreciation of assurance, having sat on approval bodies for systems. But I'm blessed in the directorate in RSSB that Anne Mills, who was up on the screen earlier, is the deputy director there, who's obviously clearly world leader in human factors. But we have a team behind Anne with that. We have a diversity of thought in the way it's structured. People who started on the footplate, people who started in police intelligence, people who've gone through the academic route and have studied at highest levels with 1 or 2 PhDs. It's the mixture, I think, that really helps in shaping the right solution. So I do think that across the piece, if I reflect it back to engineering in general, I think we need to prepare our engineers better for the wider context that we're now operating in, and probably already were, we just didn't necessarily realise it. So why can we not have some basic HF training for engineers so they know how to ask the right questions? I don't pretend to be an accountant. In fact, the qualification I hold from the ACCA requires me not to practice as an accountant because it's not the full qualification. But it enables me to ask the right questions and to understand what's coming back to me. We should be doing the same with the human factors elements as we're formulating teams, in my view.
Thank you. Claire?
I think in some instances we do what we're already doing. We bring specialists in to advise us on particular aspects of systems. We learn from them about AI and autonomous systems, and they learn from us what work in the nuclear industry is. I think that collaboration, bringing on board specialist advice and putting it with human factors experts, safety experts, engineers and users will lead us to where we want to be. I think we do need help with that because we don't understand necessarily as well as we need to what these systems could provide us and how these systems may work and how they may learn. But I think the collaboration of bringing everybody together, fully understanding our requirements, fully understanding what it means to be an operator, what it means to be a maintainer, and how they will fit into those systems is key.
Mark?
What they said.
I
mean, look, I'm biased, right? But I mean, I'm going to put my Chancellor Institute hat on now. But we need to do more of this. I mean, human factors experts need to integrate better with our engineering counterparts. I think human factors is you use the word multidisciplinary. I'd say interdisciplinary. It's the archetypal interdisciplinary subject because we do cross so many boundaries. We work with other disciplines, not alongside. We actually integrate with them. People come from psychology, biomechanics, computer science, design and engineering, and we all work together. I think what human factors brings is that unique perspective across all of those boundaries, and we can talk other languages. We learn these other areas, and we can work alongside these people and with them and help to make these systems better. Put my academic hat back on, and again echo what Chris said, more training in universities. We need more degree courses and not just independent standalone HF programs, but integrating again better with the engineering programs that are out there.
Sarah?
Yeah, so for reasons that I'm not going to claim were entirely ideological, our engineering degrees at Nottingham have had quite a lot of human factors content for a number of years, and it would be really interesting to understand what the impact on that has been. I think I would absolutely agree with my fellow panellists, but I think we also need to reflect that We mustn't fall into the trap of preaching. And Lisanne Bainbridge's paper was published in 1983. That was 41 years ago. I hope to goodness that by, I've done the maths, 2065, we're not in the same position. We need to recognise that actually the human factors profession is relatively tiny, and we can't do this on our own, and we're not going to solve this problem by simply evangelising. We need to make sure that actually the human factors profession becomes as routine for engineers to know as computational fluid dynamics. And then we need to, I think, also challenge the engineering professions in terms of the different types of specialisms that emerge. Slightly controversially, it may be that the outcome of this is that human factors doesn't end up being seen quite so much as a distinct discipline, in the same way as we don't do a degree in computational fluid dynamics. It's an automatic part of many of the degrees that we learn. And I think that we need to be a bit brave, and I really hope that our successors as presidents of the Chartered Institute are not sitting here in another 41 years' time.
Great. Right, now we started a bit late, we've used up our 30 minutes, lousy chairing, so I waive my fee. And I'm going to apologise to all of you that I'm not going to take any questions from the audience because we've got other stuff to get on, so I apologise for that. I don't doubt that some, if not all, of the panellists will be around afterwards if you want to corner them. That was absolutely fantastic. I dearly want to do a long thank you, but I'm not, because Dr. Clive Hickman, current president of the IMechE, is going to do that for us. Thank you, Clive.
Thanks, Paul. Ever the showman. Sarah, thank you for a very thought-provoking presentation day. I thought it was inspirational, but I also thought it set us all a challenge about engineers can work better with human factors experts and with the wider community. When we established the Manufacturing Technology Centre, I was motivated by the opportunities, not only of the engineering technology, but also automation, particularly intelligent automation, where the automation was able to predict itself what it was able to do. But your lecture tonight was a real reminder that all of those opportunities come with risks, and it's managing those risks which is paramount to us realising the opportunity when it arises. I'd like to thank all of our esteemed panellists and to my very good friend Paul Campion for overseeing the discussion, overrunning on time as usual, but we'll let you off tonight, I think. It's terrific to have representation from such a wide range of sectors and disciplines tonight, and we're not always in agreement, but I think we're all united in a common goal to establish and promote best engineering practice. So thank you very much indeed. I'd also like to thank Caroline for proposing and for organising this lecture. And not only that, but also for a contribution to the institution over many years and for a continued support for the years to come. Caroline has had a significant influence on our institution over the years and also over the engineering profession throughout her career. And say thank you, Caroline. And finally, I would like to invite you back onto the stage, Caroline, to give us an update on what the next steps will be with this initiative.
So, I hope everybody's enjoyed this evening. As I said in my opening remarks, it wasn't a debate. Well, you might change your mind after some of the discussion we've had, but it has been and it will be part of a wider debate. And I just wanted to say in closing, we in the institution and in IMechE are considering how we can contribute to finding solutions in engineering and issues around humans and automation. What can we do to move this whole thing forward? I think you've heard from several people this evening, there's a case to be made that we need to change, there's a case to be made that we need to collaborate. I think it's been patently clear. So how do we go around talking about and hopefully edging closer to finding the solutions around humans and automation, safety by design? If you can contribute to that debate or want to be involved, please let us know. So please take your phones out, if you have one, and use your camera to scan this QR code behind me. And this will take you to a form where you can leave your details, and it means that we get round the formalities of GDPR and we can communicate with you without getting ourselves into trouble. And we'll also distribute this form to the attendees following this event by email. Now, I also know that this, and you probably realise this has been a recorded event, and that the record will be available sometime after. Again, we encourage you to share that recording with people who haven't been here that might be in your network, and also to share that invitation, because although we don't know quite yet how we're going to do it, we're going to reflect on that in the new year, but we do want to follow through on this, along with other people who are clearly interested in trying to do the same within the engineering and broader human factors community. So thank you very much. Would you all now like to join me for refreshments down in the Marble Hall? Thank you very much.